Hello, welcome to Chapter 5, Section 6. We're doing example number 3, where we're going to analyze the quadratic equations and quadratic functions by using the discriminant. And the thing is that I've already been doing this. So in this video, we're just going to be narrowing it down and looking at it a little bit more, not strategically, a little bit more tactically. All right? Strategically means big picture, tactically means little picture. All right? So we're just looking at this one part and trying to figure out, like, well, are we going to get two distinct real solutions? Are we going to get one distinct real solution? Which basically means I got the same thing twice. They're not distinct. Distinct means different, that they're different from each other. Or are we going to get two distinct non-real complex solutions? And we've already been seeing this in the examples that we've got. All right, so basically it works out like this. When you take the discriminant, and if you get a positive number, which means it's bigger than 0, you get two real solutions that are different from each other. And the graph is going to look like this. It's going to cross the x-axis in two different places. That's what we saw when we solved it by graphing, and that's what we saw when we solved it by factoring. And sometimes we saw that when we did square roots or completing the square. Basically, any time that we got two different answers and they're both real numbers, that's what was happening. Sometimes when we factored or when we graphed it, we ended up with the same answer twice. That's what happens here. And how are we going to know that's going to happen? Because the discriminant is going to equal 0. The last thing that's going to happen is that when the discriminant is negative or less than 0, I'm going to get a graph that looks like this, so I won't be able to solve it. And if you remember, or solve it by graphing, excuse me. If you remember, I showed you that in the last video. There's one like that. Okay, so what are we going to do? We just need to find the discriminant. So notice all of these have x to the second power subtract 6x as we start. Okay, they're just trying to see that we're looking for a pattern. And this equals -7, this equals -9, this equals -11. We're going to see what's going to happen here. All right? The first thing I need to do is I need to put it in standard form. So I'm going to add I'm going to add +7 to the -7. I'm going to add +7 to both sides. So I get 0 equals x to the second power subtract 6x plus 7. For this one, I'm going to add 9 to both sides. So I get 0 equals x to the second power subtract 6x plus 9. And over here, I get 0 equals x to the second power plus 6x plus 11. Just put them in standard form. All right. I saw that these are all following kind of a pattern, so that's why I did that first step for each of them together. Now we're going to figure out the discriminant. My A is 1, my B is -6, and my C is going to be +7. Make my C a little bit better. B to the second power subtract 4AC. This is -6 to the second power subtract 4 times 1 times 7. So I'm just taking my ABC parameters and replacing them into my, I hate to use the word formula, but my rule for the discriminant. -6 times -6 is +36. 4 times 1 times 7 is 28. 36 subtract 28 is going to be 8. Now, 8 is a positive number. I'll put a plus sign in front of it. This means that I'm going to get 2, and I always get 2, but I want to make sure I say that, distinct. That means different from each other, okay? Why don't we use the word different? Because it's different from what, all right? If we say two different numbers, well, that doesn't necessarily imply that they're different from each other. So when we say distinct, that means that they are different from each other. Two distinct real zeros or solutions. Since this was an equation to start out with, we'll say roots. All right, cool, we got that. Let's see what happens with this one. So my A is still 1 and my B is still -6. This time my c is going to be positive 9. I get b to the second power, subtract 4ac, that stayed the same. Negative 6 to the second power, subtract 4 times 1 times 9. 36 subtract, wait for it, 4 times 1 times 9 is also 36. And since 36 subtract 36 is 0, I get one distinct real root. But actually, I get the same root twice. Don't forget that you always get 2. Always, always, always. You get 2. That's where the word distinct comes into play. Because these are 2 different ones from each other, you get the same thing twice over here. So I don't like the way they wrote that. By the way, why does this work? Because what's the next thing I'm going to do with the 0? I'm going to take the square root of it. The square root of 0 is 0. What does that mean? So when I do the plus or minus in front of it, positive 0, negative 0, when I add that, nothing changes. By the way, let's change this to a function and graph it. So I'm going to do x to the second power, subtract 6x plus 9. That's a perfect square trinomial, by the way. That's x subtract 3 times x subtract 3. When I graph it, the vertex touches the x-axis, and I get x equals 3, and the other one is also x equals 3. So again, I get 2 answers always, but they happen to be the same thing. All right, let's try the last one. I think you can kind of see where the pattern is going. If I go back, let me go back to this. Change this to 7. And then if I graph it, you see how it crossed twice? Probably should have done this. Those are my 2 distinct solutions. So now what do you think is going to happen with this one? If I go back and change this to 11. Aha. So my A is still 1. My B is still, whoops, excuse me. That's negative 6. And my C is now 11. So discriminant is b to the second power, subtract 4 times a times c. I get negative 6 to the second power, subtract 4 times 1 times 11. I get 36, subtract 44, which is now going to be negative 8. That tells me that I get 2 distinct, so they're both different, non-real, which means complex. Actually, this is where it always gets confusing, okay? Complex with the imaginary part, because all numbers are complex. Sorry, I should be more clear about that. 2 distinct non-real roots, because when I take the square root, the next thing I'm going to do, if I'm going to solve, is I'm going to put this under the square root sign. Square root of 8, that's good. Square root of 0, that's good. Square root of negative 8, that's going to give me an imaginary part. Okay, we'll see you in the next video.